one more problem. In this problem, they give us an overall reaction. That's this guy right here. This is our overall reaction. And then it's split up into 2 elementary steps. And then they're asking us, they give us the experimental rate law. So this is determined from the experiment. And they say, they ask, what can you say about the relative rates of the two steps of this mechanism? So like, which one's slow, which one's fast? That's what we're trying to figure out. So given the mechanism and the rate law, can you figure out which one's slow, which one's fast? Other times they give you which one's slow and fast, and you're trying to find the experimental rate law. So we're kind of working backwards a little bit here. So if I were to start this problem just by writing the rate laws for each elementary step, which again, they are dependent on the molecularity. The stoichiometry of the reaction. So this first one, I would say first rate one step, it's just going to be rate is equal to K, I'll call that K1, times reactant, right there. So I just did reactant times reactant. And then if I were to look at step 2, I'll just write that one up here, that would be like K2 times reactant. Okay, so if I look at this reaction, look at the experimental rate law, I can see that these two match. So that means that first step must be the slow step, because that's the rate determining step. And so if the experimental rate law matches the first one, then that matches the rate law of the first step, then I know that one's slow. If the second step was slow, that means the first one's fast. That gets a little bit trickier, and that's the one we're going to do next. So in this one, they give us our overall reaction. This is the overall reaction. And then they say, this is the experimentally determined rate law. So this is what we find from the experiment. And because this reaction is, as it's written, it looks like it's a termolecular, right? We have 1, 2, 3 reactants reacting at the same time. Those are pretty rare. That's probably not what's happening. And so they propose this mechanism. They say, suppose step 1 looks like this, and this one's fast, and then step 2 looks like that, and that's slow. Can we prove that this is the right rate law? Do we get this final experimental rate law from this proposed mechanism? That's what we want to do now. So what does fast mean? This first one is fast, means that it reaches equilibrium fast. That means the rate of the forward reaction, that's this guy, the rate at which NO and Br2 are coming together to form NOBr2, that rate equals the rate of the reverse reaction, where NOBr2 is split up into Br2. So if I just flip that reaction around for a second, this is the reverse reaction, right? Starting with the products, NOBr2, and making the reactants as it's written there. So I just kind of flip that around. That's the reverse reaction. So the rate of the overall reaction depends on the rate of the slow step. So let's write the rate law for the slow step. This is the rate law, slow steps. The second step is my slow step. It's right here. Let's do that in a different color, not rainbow. Let's do it in like pink, sure. So this is the slow step that I'm going to be focusing on. So rate 2 there is going to be rate will equal K2 times NOBr2 times NO. Okay. Now, the problem with that is that'd be great if I could just stop right there. But you'll see that this does not match the experimental rate law, right? That's not what we get there, because NOBr2 is an intermediate. It's made in one step and used up in another, and we can't have intermediates in our overall in our rate law, our experimentally determined rate law. It's not going to work. We can only have reactants. You can have some products. You can have a rate constant in there, but you can't have an intermediate. So now the tricky part is that we need to solve for that intermediate in terms of things that we're allowed to have in that rate law. We can have reactants, products, and rate constants. So the way we do that is we go back over to the first step. And the first step is the fast step. That means the rate of the forward reaction equals the rate of the reverse reaction. That's what we have here. The rate of the forward reaction equals the rate of the reverse reaction. So let's write those rates. Like, what's that rate law look like? So I'm going to say, rate 1 is going to be equal to the forward reaction. So going in this direction, that's going to be equal to K1, some rate constant, times NO times Br2. And then I'm going to set that equal to the reverse where I'm going to call this guy K-1. Now I'm going in this direction, and this is my reactant. So we already wrote that reverse reaction down here. So the rate law that goes with this reverse reaction is like K-1. It doesn't matter what subscript you put on there. It's just you'll have different K's. They're going to be just different constants. At the end, we're going to combine them all and get a new constant. So that's what the reverse one looks like. So I'm going to call that K minus 1 NOBr2. And that's what I'm going to try to solve for my intermediate based on that. So let me just put this where it goes in the notes, maybe. See, I'm going to bring that down here, right? So that's all we did there. So I'm setting this equal to each other. I have the rate of the forward reaction, K times the reactant times reactant, equals a different K times the product, because that's the reverse reaction. And now we'll solve for NOBr2. Okay, so I just have to isolate the intermediate, which means I just have to divide by K minus 1. All right, so K minus 1 gives me that. And so this is what NOBr2 equals, all of this stuff. I'm going to take that and plug it into the rate determining step. So where's our rate determining step? This is the rate law for our rate determining step. Oh, good. Just copy that and bring it down here. All right, so I'm going to plug that in to this step here. I'll show you what we're doing. Maybe. All right, so we've got that. NOBr2 equals all of this. So let me get rid of, like, this is what NOBr2 equals. All of everything that I have circled there. That is now going to go into our slow step where NOBr2 is. So all of this is now in there. So I end up having something that looks like K2 times all this stuff. And so times, I've got all that. I've got K1 over K negative 1, NO, BR2 times NO. Now, if I want to combine things to make this look a little bit prettier, I have K times K divided by K. Combine all those K's. This is just one new K. And then I have NO and NO. That's NO squared times BR2. And then that is the rate law according to this proposed mechanism. And if you look up here, that is the experimental rate law that they gave us. So the whole point of this problem was just to verify that that's true. So they gave us an overall reaction. They split it up into mechanisms. They said one's slow, one's fast. For the slow one, that's the rate determining step, but it has an intermediate in it. So we had to go up to the first step and say, well, fast means it reaches equilibrium fast. At equilibrium, the rate of the forward reaction equals the rate of the reverse reaction. So I wrote the rate law for the forward reaction. I wrote the rate law for the reverse reaction. I set them equal, and I solved for that intermediate. So that's what we did down here. We set the rate forward equal rate reverse. We solved for the intermediate, and then we took that intermediate, whatever all that equals. It's going to be a mixture of rate constants and concentrations of reactants against products. Take that, put it into the slow step, and then just combine like